In universal algebra and in model theory, a structure consists of a set along with a collection of finitary operations and relations that are defined on it. Universal algebra studies structures that generalize the algebraic structures such as groups, rings, fields and vector spaces. The term universal algebra is used for structures with no relation symbols. Model theory has a different scope that encompasses more arbitrary theories, including foundational structures such as models of set theory. From the model theoretic point of view, structures are the objects used to define the semantics of first-order logic. For a given theory in model theory, a structure is called a model, if it satisfies the defining axioms of that theory, although it is sometimes disambiguated as a semantic model when one discusses the notion in the more general setting of mathematical models. Logicians sometimes refer to structures as interpretations. In database theory, structures with no functions are studied as models for relational databases, in the form of relational models. Definition. Formally, a structure can be defined as a triple A equals A sigma I display style mathcal A equals A sigma I, consisting of a domain a signature sigma, and an interpretation function I that indicates how the signature is to be interpreted on the domain. To indicate that a structure has a particular signature sigma, one can refer to it as a sigma structure. Domain. The domain of a structure is an arbitrary set. It is also called the underlying set of the structure, its carrier, especially in universal algebra, or its universe, especially in model theory. In classical first-order logic, the definition of a structure prohibits the empty domain. Sometimes the notation DOM display style operator name DOM mathcal A or display style mathcal A is used for the domain of A display style mathcal A, but often no notational distinction is made between a structure and its domain, i.e. the same symbol A display style mathcal A refers both to the structure and its domain. Signature. The signature sigma equals S R display style sigma equals S operator name R of a structure consists of a set S display style S of function symbols and relation symbols along with a function R S n 0 display style text R S to math b n underscore 0 that ascribes to each symbol S a natural number n equals R S display style n equals operator name R S, which is called the arity of S because it is the arity of the interpretation of S. Since the signatures that arise in algebra often contain only function symbols, a signature with no relation symbols is called an algebraic signature. A structure with such a signature is also called an algebra. This should not be confused with the notion of an algebra over a field. Interpretation function. The interpretation function I of A display style mathcal A assigns functions and relations to the symbols of the signature. Each function symbol f of arity n is assigned an nary function f a equals I F display style F caret mathcal equals I F on the domain. Each relation symbol R of arity n is assigned an NARY relation R A equals I R A R R display style R caret mathcal equals I R subset A caret operator name R on the domain. A nullary function symbol C is called a constant symbol, because its interpretation I C can be identified with a constant element of the domain. When a structure and hence an interpretation function is given by context, no notational distinction is made between a symbol S and its interpretation is. For example, if f is a binary function symbol of a display style mathcal one simply writes f a 2 display style f mathcal caret 2 right arrow mathcal rather than f a 2 display style f caret mathcal caret 2 right arrow mathcal topic examples. The standard signature sigma f for fields consists of two binary function symbols plus and times, where additional symbols can be derived, such as a unary function symbol uniquely determined by plus and the two constant symbols 0 and 1 uniquely determined by plus and times respectively. Thus a structure algebra for this signature consists of a set of elements A together with two binary functions, that can be enhanced with a unary function, and two distinguished elements, but there is no requirement that it satisfy any of the field axioms. The rational numbers Q, the real numbers R and the complex numbers C, like any other field, can be regarded as sigma structures in an obvious way. Q equals Q sigma F I Q display style mathcal Q equals Q sigma underscore F I underscore mathcal Q R equals R sigma F I R display style mathcal R equals R sigma underscore F I underscore mathcal R C equals C sigma F I C display style mathcal C equals C sigma underscore F I underscore mathcal C. In all three cases we have the standard signature given by sigma F equals S F R F display style sigma underscore F equals S underscore F operator name R underscore F with S F equals plus times minus 0 1 display style S underscore F equals plus times 0 1 R F plus equals R F times equals 2 R F minus equals 1 R F 0 equals R F 1 equals 0. Display style operator name R underscore F plus equals operator name R underscore F times equals 2 operator name R underscore F equals 1 operator name R underscore F 0 equals operator name R underscore F 1 equals 0. Interpretation functions I Q plus Q times Q display style I underscore mathcal Q plus colon Q times Q to Q is addition of rational numbers I Q times Q times Q display style I underscore mathcal Q times colon Q times Q to Q is multiplication of rational numbers I Q minus Q display style I underscore mathcal Q colon Q to Q is the function that takes each rational number x to x and I Q 0 element of Q display style I underscore mathcal Q 0 in Q is the number 0 and I Q 1 element of Q display style I underscore mathcal Q 1 in Q is the number 1 and I R display style I underscore mathcal R and IC display style I underscore mathcal C are similarly defined, but the ring Z of integers, which is not a field, is also a sigma F structure in the same way. In fact, there is no requirement that any of the field axioms hold in a sigma F structure. A signature for ordered fields needs an additional binary relation such as the ordinary signature for set theory includes a single binary relation element of. A structure for this signature consists of a set of elements and an interpretation of the element of relation as a binary relation on these elements. Induced substructures and closed subsets. Display style mathcal A is called an induced substructure of B. Display style mathcal B if a display style mathcal A and B display style mathcal B have the same signature sigma equals sigma B display style sigma mathcal A equals sigma mathcal B. The domain of A display style mathcal A is contained in the domain of B display style mathcal B A B display style mathcal A subsetek mathcal B and the interpretations of all function and relation symbols agree on B display style mathcal B. The usual notation for this relation is a B display style mathcal A subsetek mathcal B. A subset B display style B subsetek mathcal A of the domain of a structure display style mathcal A is called closed if it is closed under the functions of A display style mathcal a, i.e. if the following condition is satisfied, for every natural number n, every nary function symbol f in the signature of a display style mathcal a, and all elements b 1 b 2 b n element of b display style b underscore 1 b underscore 2 dots b underscore n in B, the result of applying f to the n tuple b 1 b 2 b n display style b underscore 1 b underscore 2 dots b underscore n is again an element of B f b 1 b 2 b n element of B display style f b underscore 1 b underscore 2 dots b underscore n in B. For every subset B display style b subset ek mathcal a, there is a smallest closed subset of a display style mathcal a that contains B. It is called the closed subset generated by B, or the hull of B, and denoted by B display style Langle B wrangle or B a display style Langle B wrangle underscore mathcal a. The operator display style Langle wrangle is a finitary closure operator on the set of subsets of a display style mathcal a. If a equals a sigma I display style mathcal a equals a sigma I and b a display style b subset ek a is a closed subset, then b sigma I display style b sigma I is an induced substructure of a display style mathcal a, where I display style I assigns to every symbol of sigma the restriction to be of its interpretation in a display style mathcal a. Conversely, the domain of an induced substructure is a closed subset. The closed subsets or induced substructures of a structure form a lattice. The meet of two subsets is their intersection. The join of two subsets is the closed subset generated by the union. Universal algebra studies the lattice of substructures of a structure in detail. Topic: Examples. Let sigma equals plus times minus 0 1 be again the standard signature for fields. When regarded as sigma structures in the natural way, the rational numbers form a substructure of the real numbers, and the real numbers form a substructure of the complex numbers. The rational numbers are the smallest substructure of the real or complex numbers that also satisfies the field axioms. The set of integers gives an even smaller substructure of the real numbers which is not a field. Indeed, the integers are the substructure of the real numbers generated by the empty set, using this signature. The notion in abstract algebra that corresponds to a substructure of a field, in this signature, is that of a subring, rather than that of a subfield. The most obvious way to define a graph is a structure with a signature sigma consisting of a single binary relation symbol e. The vertices of the graph form the domain of the structure, and for two vertices A and B, A B element of E display style A B in text E means that A and B are connected by an edge. In this encoding, the notion of induced substructure is more restrictive than the notion of subgraph. For example, let G be a graph consisting of two vertices connected by an edge, and let H be the graph consisting of the same vertices but no edges. H is a subgraph of G, but not an induced substructure. The notion in graph theory that corresponds to induced substructures is that of induced subgraphs. Homomorphisms and embeddings. Homomorphisms. Given two structures display style mathcal A and B display style mathcal B of the same signature sigma, a sigma homomorphism from A display style mathcal A to B display style mathcal B is a map H A B display style H mathcal A right arrow mathcal B that preserves the functions and relations. More precisely, for every NARY function symbol f of sigma and any elements a 1 a 2 a n element of a display style r underscore 1 r underscore 2 dots r underscore n in mathcal A. The following equation holds: H F A 1 A 2 A N equals F H A 1 H A 2 H A N display style H F A underscore 1 R underscore 2 dots R underscore N equals F H A underscore 1 H A underscore 2 dots H A underscore N. For every NARY relation symbol R of sigma and any elements a 1 a 2 a n element of a display style r underscore 1 r underscore 2 dots r underscore n in mathcal A. The following implication holds: a 1 a 2 a n element of R H A 1 H A 2 H A n element of R display style R underscore 1 R underscore 2 dots R underscore n in R implies H A underscore 1 H A underscore 2 dots H A underscore n in R. The notation for a homomorphism H from a display style mathcal A to B display style mathcal B is H A B display style H mathcal A right arrow mathcal B. For every signature sigma there is a concrete category sigma hom which has sigma structures as objects and sigma homomorphisms as morphisms. A homomorphism H A B display style H mathcal a right arrow mathcal B is sometimes called strong if for every NARY relation symbol R and any elements B 1 B 2 B n element of B display style B underscore 1 B underscore 2 dots B underscore n in mathcal B such that B 1 B 2 B n element of R display style B underscore 1 B underscore 2 dots B underscore n in R. There are a 1 a 2 a n element of a display style R underscore 1 R underscore 2 dots R underscore n in mathcal a such that a 1 a 2 a n element of R display style R underscore 1 R underscore 2 dots R underscore n in R and B 1 equals H A 1 B 2 equals H A 2 B n equals H A n display style B underscore 1 equals H A underscore 1 B underscore 2 equals H A underscore 2 dots B underscore n equals H A underscore n. The strong homomorphisms give rise to a subcategory of sigma hom. Topic: Embeddings. A sigma homomorphism H A B display style H mathcal a right arrow mathcal B is called a sigma embedding if it is 1-to-1 and for every NARY relation symbol R of sigma and any elements a 1 a 2 a n display style R underscore 1 R underscore 2 dots R underscore n. The following equivalence holds: a 1 a 2 a n element of R H A 1 H A 2 H A n element of R display style R underscore 1 R underscore 2 dots R underscore n in R IFF H A underscore 1 H A underscore 2 dots H A underscore n in R. Thus an embedding is the same thing as a strong homomorphism which is 1-to-1. The category sigma EMB of sigma structures and sigma embeddings is a concrete subcategory of sigma hom. Induced substructures correspond to subobjects in sigma EMB. If sigma has only function symbols, sigma EMB is the subcategory of monomorphisms of sigma hom. In this case, induced substructures also correspond to subobjects in sigma hom. Topic: Example. As seen above, in the standard encoding of graphs as structures, the induced substructures are precisely the induced subgraphs. However, a homomorphism between graphs is the same thing as a homomorphism between the two structures coding the graph. In the example of the previous section, even though the subgraph H of G is not induced, the identity mapped Hg is a homomorphism. This map is in fact a monomorphism in the category sigma hom, and therefore H is a subobject of G which is not an induced substructure. Topic: Homomorphism problem. The following problem is known as the homomorphism problem. Given two finite structures display style mathcal and b display style mathcal b of a finite relational signature, find a homomorphism H A B display style H mathcal a right arrow mathcal B, or show that no such homomorphism exists. Every constraint satisfaction problem (CSP) has a translation into the homomorphism problem. Therefore, the complexity of CSP can be studied using the methods of finite model theory. Another application is in database theory, where a relational model of a database is essentially the same thing as a relational structure. It turns out that a conjunctive query on a database can be described by another structure in the same signature as the database model. A homomorphism from the relational model to the structure representing the query is the same thing as a solution to the query. This shows that the conjunctive query problem is also equivalent to the homomorphism problem. Topic: Structures and first-order logic. Structures are sometimes referred to as first-order structures. This is misleading, as nothing in their definition ties them to any specific logic, and in fact they are suitable as semantic objects both for very restricted fragments of first-order logic such as that used in universal algebra, and for second-order logic. In connection with first-order logic and model theory, structures are often called models, even when the question, "models of what?" has no obvious answer. Topic: Satisfaction relation. Each first-order structure M display style mathcal M has a satisfaction relation M phi display style mathcal M v dash phi, defined for all formulas phi display style phi in the language consisting of the language of M display style mathcal M, together with a constant symbol for each element of M, which is interpreted as that element. This relation is defined inductively using Tarski's T-schema. A structure M display style mathcal M is said to be a model of a theory T if the language of M display style mathcal M is the same as the language of T and every sentence in T is satisfied by M display style mathcal M. Thus, for example, a ring is a structure for the language of rings that satisfies each of the ring axioms, and a model of ZFC set theory is a structure in the language of set theory that satisfies each of the ZFC axioms. Topic: Definable relations. An NARY relation R on the universe M of a structure M display style mathcal M is said to be definable or explicitly definable, or display style empty set definable if there is a formula phi x1 xn such that R equals 1 a n element of m n m phi 1 a n display style R equals R underscore 1 L dots R underscore n in M caret n math cal M V dash var phi R underscore 1 L dots R underscore n. In other words, R is definable if and only if there is a formula phi such that a 1 a n element of R M phi a 1 a n display style R underscore 1 L dots R underscore n in R left right arrow math cal M V dash var phi R underscore 1 L dots R underscore n is correct. An important special case is the definability of specific elements. An element M of M is definable in M display style math cal M if and only if there is a formula phi x such that M x x equals M left right arrow phi x display style math cal M V dash for x x equals M left right arrow var phi x. Topic: Definability with parameters. A relation R is said to be definable with parameters or M display style math cal M definable if there is a formula phi with parameters from M display style math cal M such that R is definable using phi. Every element of a structure is definable using the element itself as a parameter. It should be noted that some authors use definable to mean definable without parameters, while other authors mean definable with parameters. Broadly speaking, the convention that definable means definable without parameters is more common amongst set theorists, while the opposite convention is more common amongst model theorists. Implicit definability. Recall from above that an NARY relation R on the universe M of a structure M _mathcal M is explicitly definable if there is a formula phi x1 xn such that R equals 1 a n element of M n M phi 1 a n display style R equals R underscore 1 L dots R underscore n in M caret n math cal M V dash var phi R underscore 1 L dots R underscore n. Here the formula phi used to define a relation R must be over the signature of M display style math cal M, and so phi may not mention R itself, since R is not in the signature of M display style mathcal M. If there is a formula phi in the extended language containing the language of M display style mathcal M and a new symbol R, and the relation R is the only relation on M display style mathcal M such that M phi display style mathcal M V dash var phi, then R is said to be implicitly definable over M display style mathcal m. By Beth's theorem, every implicitly definable relation is explicitly definable. Topic: Many sorted structures. Structures as defined above are sometimes called one-sorted structures to distinguish them from the more general many-sorted structures. A many-sorted structure can have an arbitrary number of domains. The sorts are part of the signature, and they play the role of names for the different domains. Many sorted signatures also prescribe on which sorts the functions and relations of a many-sorted structure are defined. Therefore, the arities of function symbols or relation symbols must be more complicated objects such as tuples of sorts rather than natural numbers. Vector spaces, for example, can be regarded as two-sorted structures in the following way. The two-sorted signature of vector spaces consists of two sorts V for vectors and S for scalars and the following function symbols. If V is a vector space over a field F, the corresponding two-sorted structure V \mathcal V consists of the vector domain V equals V \mathcal V underscore V equals V. The scalar domain V S equals F \mathcal V underscore S equals F, and the obvious functions, such as the vector 0 V equals 0 element of V display style 0 underscore V caret mathcal V equals 0 in mathcal V underscore V. The scalar 0 S V equals 0 element of V S display style 0 underscore S caret mathcal V equals 0 in mathcal V underscore S, or scalar multiplication times V S times V display style times caret mathcal V underscore S times mathcal V underscore V right arrow mathcal V underscore V. Many sorted structures are often used as a convenient tool even when they could be avoided with a little effort. But they are rarely defined in a rigorous way, because it is straightforward and tedious, hence unrewarding, to carry out the generalization explicitly. In most mathematical endeavors, not much attention is paid to the sorts. A many-sorted logic however naturally leads to a type theory. As Bart Jacobs puts it, "A logic is always a logic over a type theory." This emphasis in turn leads to categorical logic because a logic over a type theory categorically corresponds to one total category, capturing the logic, being fibered over another base category, capturing the type theory. Other generalizations. Partial algebras. Both universal algebra and model theory study classes of structures or algebras that are defined by a signature and a set of axioms. In the case of model theory, these axioms have the form of first-order sentences. The formalism of universal algebra is much more restrictive, essentially it only allows first-order sentences that have the form of universally quantified equations between terms, e.g. display style forall x display style forall y x plus y equals y plus x. One consequence is that the choice of a signature is more significant in universal algebra than it is in model theory. For example, the class of groups, in the signature consisting of the binary function symbol times and the constant symbol 1, is an elementary class, but it is not a variety. Universal algebra solves this problem by adding a unary function symbol -1. In the case of fields, this strategy works only for addition. For multiplication it fails because 0 does not have a multiplicative inverse. An ad hoc attempt to deal with this would be to define 0-1. 0. This attempt fails, essentially because with this definition 0 times 0-1 1 is not true, therefore, 1 is naturally led to allow partial functions, i.e., functions that are defined only on a subset of their domain. However, there are several obvious ways to generalize notions such as substructure, homomorphism and identity. Structures for typed languages. In type theory, there are many sorts of variables, each of which has a type. Types are inductively defined. Given two types delta and sigma, there is also a type sigma delta that represents functions from objects of type sigma to objects of type delta. A structure for a typed language in the ordinary first-order semantics must include a separate set of objects of each type, and for a function type the structure must have complete information about the function represented by each object of that type. Higher-order languages. There is more than one possible semantics for higher-order logic, as discussed in the article on second-order logic. When using full higher-order semantics, a structure need only have a universe for objects of type 0, and the T-schema is extended so that a quantifier over a higher-order type is satisfied by the model if and only if it is disquotationally true. When using first-order semantics, an additional sort is added for each higher-order type, as in the case of a many-sorted first-order language. Structures that are proper classes. In the study of set theory and category theory, it is sometimes useful to consider structures in which the domain of discourse is a proper class instead of a set. These structures are sometimes called class models to distinguish them from the set models discussed above. When the domain is a proper class, each function and relation symbol may also be represented by a proper class. In Bertrand Russell's Principia Mathematica, structures were also allowed to have a proper class as their domain. See also: Mathematical structure. Notes